Hello everybody, welcome. So we are in our last part of module 4, that is moving load and influence lines. So a small recap what we have studied so far. So we saw about the basics of influence lines, what is the need for influence lines and why is it necessary. Then we divided our syllabus into three parts. One is the basics, then two parts. The first is the simply supported beam and the second one is the overhang beam. And we saw for simply supported beam the influence line diagram for the reactions at A and B, shear forces, that is influence line diagram for positive shear force, influence line diagram for the negative shear force, absolute maximum shear force, absolute maximum negative shear force, and maximum bending moment and absolute maximum bending moment. So simply supported beams are over. We have seen some problems also. Now we are going for overhang beam. So in overhang we have two cases. Case 1 is influence line diagram for single sided overhang beam and case 2 is influence line diagram for double sided overhang. So we will go for case 1 first, that is influence line diagram for single sided overhang beam. So this is called single sided overhang beam. See, we call this as a single sided overhang beam because on one side we have an overhang. This BC is our overhang. So we call it as a single sided overhang beam. Now this beam is of length L. We have a unit load 1 kilonewton is moving from A to C. So first case we will be finding the influence, how to find the influence line diagram for reaction RA. So for finding the reaction RA we apply sigma MB is equal to 0. So by applying sigma MB is equal to 0 we get RA is equal to L minus X by L, because RA into L is equal to 1 into L minus X. So we get RA is equal to L minus X by L. Now the varying factor is X, and this X varies from A to B when the unit load is in portion AB. The condition is unit load is in portion AB. See, we can see here unit load is in portion AB. So when the unit load is in the portion AB, X varies from A to B, that is X is equal to 0 to X is equal to L. So at A, X is equal to 0 and RA is equal to 1 by applying X is equal to 0. And at B, by applying X is equal to L, we get RA is equal to 0. Now we will go on for the next part, that is when this 1 kilonewton load is in BC. Okay, so this 1 kilonewton load is in the portion BC and we are taking this X at a distance of, this unit load is at a distance X from C. C is our origin. So for this portion, X is equal to 0 at C and X is equal to A at B. We are finding sigma MB is equal to 0. So we get RA is equal to minus A minus X by L. X varies from 0 to A, from C to B. So 0 to A. At C, X is equal to 0 and RA is minus A by L. And at B, X is equal to A and RA is equal to 0. Now we will draw the influence line diagram. So already we have found the values at A, at B for the portion AB. Now when the unit load is in the portion BC, what is the magnitude at C and intensity at B? So we will draw the influence line diagram for RA, reaction A. So when the load is in the portion AB, at A, that is the reaction A at A is equal to 1. Then when at B it is 0. Now when the load is in the portion BC, at B RA is equal to 0 and at C, RB is equal to, RA is equal to minus A by L. This is minus A by L. So remember, see, we all know how to draw the influence line diagram for shear force at A. The maximum ordinate will be equal to 1 and at B it will be 0. Just extend this line. Just extend this line to A by L. This ordinate is A by L. Remember, this ordinate is A by L. Similarly, we will see how to draw the influence line diagram for RB. So, for drawing the influence line diagram for RB, two parts. From A to B, unit load is from A to B, unit load is moving from B to C. So, we take sigma MA is equal to 0. Therefore, we get RB is equal to X by L. X is varying from 0 to, from A to B. That is, X is varying from 0 to L. So, at A, RB is equal to 0 and at B, RB is equal to 1. Now, the load is in the portion BC. Unit load is in the portion BC. When the unit load is in the portion BC, our X is varying from C to B. That is, from here it is 0 to A. So, we are applying sigma MA is equal to 0. We get RB is equal to L minus L plus A minus X by L. Now, X is varying from 0 to A. At C, X is equal to 0. By applying X is equal to 0, we get RB is equal to L plus A by L. That is nothing but, so this is equal to 1 plus A. 1 that is equal to, I will write here 1 plus A. Now, at B, X is equal to A and RB is equal to 1. So, our influence line diagram for RB, at A it is 0, at B it is 1. When the unit load is in the portion BC, at B it is 1 and at C it is 1 plus A. So, this is equal to 1 plus A. This is equal to 1 plus A. So, remember, we know for a simply supported beam, RB, for the influence line diagram for RB varies from 0 at A to 1 at B. Just extend this to 1 plus A. That's all. So, we will draw both the influence line diagrams in the same page. Influence line diagram for RA. See, this is the case for simply supported beam. Just extend this for the intensity of A by L. Here, we know this is the case. Now, just extend this in the portion of the overhang for 1 plus A. Now, we will go for finding the influence line diagram for shear force. For shear force is always taken at a section. So, for this case, our section is taken at D. And we have three portions. That is, our unit load is varying from A to D, D to B and B to C. So, three portions. We have three portions. Unit load is in the portion AD, unit load is in the portion DB and unit load is in the portion BC. Now, this unit load, when it is taken in the region AD, this is taken at a distance Z from A. So, when it is from when it is at a distance of Z from A, we apply sigma MA is equal to 0, we get RB is equal to Z by L. So, Z is varying from 0 to X. 0 to x. So at A, Z is equal to 0, and RB, substituting Z is equal to 0, we get RB is equal to 0. Substituting Z is equal to x at D, we get RB, FD is equal to, that is the shear force at D is equal to minus RB is equal to minus x by L. See, I forgot to tell you one thing. When you are determining the influence line diagram or shear forces, we know by definition, shear force is the summation of all the forces either to the right or to the left of the section. So now when we take our section as D, when we take this as our section, when the load is moving, when the load is on the left of the section, when the load is on the left of the section, we will take summation of all the forces to the right of the section. When the load is on the right of the section, we will consider the summation of all the forces to the left of the section. Here, when the unit load is moving from A to D, the unit load is on the left of the section, so we will consider the forces to the right of the section. When the unit load is in the region DB and BC, the unit load is on the right of the section, so we will consider the summation of all the forces to the left of the section. And we know when we are considering a section, the forces on the left upwards and the forces on the right which are downwards is taken as positive. And when we are considering a section, the left downward forces and the right upward forces is considered as negative. So, it is RB is to the right of the section. So, right upward force is taken as negative. That is why it is minus RB. Now, when the load is on the portion DB, when the load is in the portion DB. So, when the load is in this portion, the load is on the right of the section, we will consider all the forces, a summation of all the forces on the left of the section, that is RA, only RA. RA is left upwards, we will take it as positive. So, anywhere from D to C, our shear force at the section will be equal to RA. So, we apply to find RA, we apply sigma MB is equal to 0. This Z is taken at a distance, Z is taken from A. From A. Z is the distance of the unit load taken from A. So, by applying sigma MB is equal to 0, we get RA into L. This RA into L. RA into L minus, this is anti-clockwise. So, minus this 1 into this distance. So, this distance is L minus Z is equal to 0. We get RA is equal to L minus Z by L. So, Z is varying from, now you see Z is varying from X to L. This is from D to B. So, X to L. So, by substituting we get at D RA is equal to L minus X and at B RA is equal to 0. Influence line diagram, that is when the unit load is in the portion BC. So, it is on the right of the section. So, we will consider all the forces to the left of the section. So, shear force at D will be equal to RA. So, we find sigma MB, by applying sigma MB is equal to 0, we get RA is equal to minus A minus Z by L or Z minus A by L. So, Z varies from 0 to A. 0 at C and A at B. So, at C, Z is equal to 0. At C, Z is equal to 0. We get FD is equal to RA, that is equal to minus A by L. And at B, Z is equal to A and we get FD is equal to RA is equal to 0. So, we had three parts. X varying from 0 to x. This is our first part. Z varying from x to L was our second part. Z varying from 0 to A is our third part. So, when the unit load is in the first part, that is from 0 to x, Z varies from 0 to x, at A, shear force is equal to 0, at D, shear force at the section is equal to minus x by L. So, minus is plotted downwards. So, from 0 to minus x by L. So, we will plot it from 0 to minus x by L, 0 to x by L. Now, we will come to the second part. So, this is the second part. Z varies from D to B, from D to B. So, at D, L minus x by L, at B it is 0. So, we have to start at D it is L minus x by L, and at B it is 0. At D it is L minus x by L, and at B it is 0. Now we will join these two lines, because when there is a unit load at a section, there is a drop or a rise. So here it is a rise from negative to positive. Now third portion, that is when the unit load is in the portion BC, from C to B. So at C the value is A by L, minus A by L, and at B it is a 0. So we will draw the line from minus A by L to 0. Then we will join this line. So this is the influence line diagram for the section at X, section at D. Now the influence line diagram for the bending moment at the section. So for bending moment also, because we are considering the section, now we have three parts from A to D, D to B, and B to C. Same way, for bending moment, we have only positive ordinates, because when we are considering a section, the left clockwise and the right anti-clockwise is taken as positive. So this is taken as positive. So we have only positive ordinates, because when we are taking this section, when the unit load is in the left of the section, we will consider right. It is RB into D. RB into D. So right anti-clockwise, positive. When the unit load is in the right of the section, that is RA into D, left clockwise, that is also positive. So only positive ordinates. Now, same way as we saw in the shear force, Z varies from 0 to X. The bending moment is RB into L minus X, RB into L minus X, shear force. So substituting X is equal to 0, at A we get bending moment is equal to 0. Substituting Z is equal to X, at D we get bending moment is equal to X by L into L minus X. Similarly, when the unit load is in the portion DB, we take sigma MB is equal to 0 to find RA, because it is to the right of the section. Because the unit load is to the right of the section, we will consider the moments, summation of moments to the left of the section. So at D, Z is varying from X to L, and the bending moment is equal to RA into X, RA into X. This RA into this distance X. So we will get MD. Now when the unit load is in the portion BC, unit load is to the right of the section, so we will consider the summation of moments to the left of the section, that is RA into X. So RA into X. So find RA, substitute the values for A is Z is varying from 0 to A. Z varies from, Z is varying from 0 to A. So we are substituting and finding the value. Now, so the first part, this is the first part from 0 to X. The value for bending moment is 0 to X by L into L minus X. So we are drawing the bending moment. So that is equal to 0 from 0. It starts from 0 to x by L into L minus x. Now come to the second portion. Z is varying from x to L. The variation is from x by L into L minus x to 0. So x by L into L minus x to 0. Now coming for the third portion, Z varies from 0 to A. The value is minus AX by L to 0. So the variation is from minus AX by L to 0. Since this is minus AX by L. So this is the bending moment diagram. See, just what we will do is, we know this is the bending moment diagram for the simply supported beam. Just extend this line. Since it is an overhang, just extend this line and remember the ordinate. It is A by L into X. A by L into X. Since it is this overhang is on the right of the section, it is A by L into X. So that's all case 1. So similarly for a double-sided overhang beam, we will go little fast. When it is a double-sided overhang beam, we will have two overhangs. First overhang is BC and the second overhang is AD. We will take this distance as A and this distance as B. All the remaining concepts are same. We are applying sigma m, our unit load is moving from D to A. First our moving load is moving from D to A, then from A to B, then from A to B and then from B to C. So we have three portions. So for the first portion, apply sigma MB is equal to 0. We get RA is equal to L plus B minus X by L. X is varying from 0 to B. So apply X is equal to 0 and X is equal to B. Find the value for RA at D and RA at B. That is 1 plus B by L. Now when the unit load is in the portion AB, find RA. X is varying from B to L plus B. B to L plus B. Substitute and find the values. Now when the unit load is in the portion BC, find RA and X is varying from 0 to A. So we will substitute the values from 0 to A and we are finding the values of RA. Now we will draw the influence line diagram for the shear force at reaction RA. So this is the first portion. So totally we have three portions. First portion is varying from 0 to B. It is 1 plus B to 1. So here it is 1 plus B to 1. 1 plus B to 1. And for the second portion, that is when the unit load is in the second portion, A to B, X is varying from B to B minus B plus L, B to B plus L, because L is the span length of AB. So X is varying from B to B plus L. Substituting we get 1 and 0. So it starts from 1, end in 0. Now for the third portion, X varies from 0 to A and the values are minus A by L and 0. This is A by L, 0. So we know, that's all. See, it's very simple to remember. We know this is the case for simply supported beam. For the right side of the overhang, just extend this line. This is A by L. For the left side also extend this line. This is 1 plus B. This is B. So 1 plus B. Same way, influence line diagram for reaction RB. So when the unit load is in the portion DA, we are applying sigma MA is equal to 0 and find what is RB. Substitute X varies from 0 to B. Substitute the values for X and we get RB is equal to minus B by L and RA is equal to 0. Now when the unit load is in the portion AB, unit load is in the portion AB, find sigma MA is equal to 0. So RB is equal to x minus B by L. X is varying from B to B plus L. So the values for RB is 0 and at x is equal to B plus L it is 1. Now when the unit load is in the portion BC, the values for RB is from 1 plus A to 1. Now we will draw the influence line diagram. So first case, that is when x varies from 0 to B, the values are minus B by L and 0. So it is minus B by L to 0. Second case, x varies from B to B plus L. The values are at A, RB is equal to 0, at B, RB is equal to 1. So at A, RB is equal to 0, at B, RB is equal to 1. Now for the third region, when x is varying from 0 to A, at C, x is equal to 0 and RB is equal to 1 plus A. At B, x is equal to A and RB is equal to 1. So it is 1 plus A to 1. Now influence line diagram both together for RA and RB. Influence line diagram of shear force for the section XX. So when the load is in the portion, so here this is our section. So we have 4 parts. When the unit load is in DA, when the unit load is from DA, AX, when the unit load lies between XB and when the unit load lies between BC. Now first part is when the unit load lies in DA, Z is varying from 0 to B. Z is taken as the distance of unit load from D. So we find RB is equal to Z minus B by L. Substitute Z is equal to 0, we get minus RB is equal to B by L. Substitute Z is equal to B, we get Fx, shear force at X is equal to minus RB is equal to 0. Similarly, when the load is in the portion AX, second part, so the load is on the left of the section, we have to find RB. So apply sigma MA is equal to 0, we get RB is equal to X minus B by L. RB is equal to Z minus B by L. So Z varies from B to X plus B. Substituting the values, we get the shear forces at A and at X for the section X. When the unit load is from X to B, so unit load is in the region X to B. So now the unit load is on the right of the section, so we will find RA. So the shear force at X will be equal to plus RA. So substitute the values for Z and find the values of shear force at X. Now last portion, when the unit load is in the portion BC. So sigma MB is equal to 0, we get RA is equal to minus A minus Z by L or Z minus A by L. So at C, Z is equal to 0 and at B, Z is equal to A. By substituting, we get the values for shear force Fx is equal to minus A by L and 0. Now, first part, that is when the unit load is in DA. When the unit load is in DA, the values are B by L and 0. This is positive, not negative, positive. So B by L, from B by L to 0. When the unit load is in the portion AX, that is X is varying from second part B to X plus B. At A, shear force is equal to 0 and at X, shear force is equal to minus X by L. So, from 0 to minus X by L. Now, third portion, Z varies from X plus B to B plus L. X plus B to B plus L. That is from X to B. The variation is L minus X by L to 0. So, it is from L minus X by L to 0. Since at the section there is a rise. Now, for the fourth portion from 0 to A, it is minus A by L to 0. So, this is the influence line diagram for shear force. Now, influence line diagram for bending moment at the section XX. Same way, concept is the same. The only thing is we will multiply the shear force by its distance. And both are positive. Because left clockwise and right anti-clockwise is positive. Now, Z varies from 0 to B. That is, for the first, when the unit load is in dA, the values are minus B by L into L minus X and 0. When the unit load, second part, when the unit load is in AX, the values of moment are from 0 to X by L into L minus X. When the unit load is in the portion XB, the moment varies from X by L into L minus X to 0. When the unit load is in the portion BC, it varies from minus A by L into X to 0. So, we will take all the four parts together. First part, when X varies from 0 to B, that is the first part. That is minus B by L into L minus X to 0. Now, second part, Z varies from B to X plus B. This is the second part. So, variation is from 0 to X by L into L minus X. Now, third part, Z varies from X plus B to B plus L. So, variation is from X by L into L minus X to 0. Fourth part, Z varies from 0 to A. The values are A by L into X to 0. Thank you. Hope you all understood. If you have doubts, you can comment on the section. Only thing is, all the influence line diagram are similar to that of simply supported beam. For overhang portion, just extend the influence lines. Thank you.